Okay, good morning. Yeah, it's land acknowledgement. It's something that's becoming more common in
And that actually makes
countries
sense.
that have the colonial history. Like
But it
Australia,
hallucinates syntax.
And it's an acknowledgement that, where we live and work used to belong
I mean,
to people, and we kicked them out, or, yeah. Okay, good morning, everyone. Good morning. It's not so common in the US, but it's more common in Canada and Australia. So I will not say much because we all know each other very well. I would just remind that this workshop is organized through the Institute of Advanced Studies. We had a group on the history and philosophy of computability in 2016. And it is a sort of also a reunion. So this is one thing. Two, very and of course, thanks to all of you who came here. I hope that you will have a wonderful week. Maybe two quick notes. One is that if you want to send in advance your PowerPoint presentation to Anat, the one who wrote you all kinds of emails, the organizer here, so you can send her, and they will put it on a stick, like it will be ready if you send it to her a day in advance. Another thing is that if any one of you needs like a room or something for Zooming with the outside world, etc., so you can approach me. I have a key to a room. I think it's 118 or 108. I will look. But just know that it is a possibility. And so again, enjoy the workshop. And Nir. Hi, Nahum. You are our chair, please.
Yeah, I'm not sure why I'm standing, so welcome everyone. Gualtiero here is not someone that needs much introduction, but I thought I'll introduce him anyway. So Gualtiero is from the University of Missouri St. Louis. He's going to talk to us about the physical signature of computation, joint work with Neil Anderson. You might know that Gualtiero wrote a paper or two or 500 on computation, and we're all very excited to hear his talk. So we're going to aim for something like 40-minute discussion and then 20-minute Q&A. Okay, I'll try to be strict.
40-minute presentation.
Yeah, 40-minute presentation, 20-minute Q&A. You get the drift. Thank you.
Well, thank you. Everyone, thanks to the organizers for inviting me. It's lovely to be back here. And thanks everyone for coming. This is presenting joint work with Neil, who calls himself a physical information theorist. So he is one of the main people who has developed the work from the thermodynamics of computation, Landauer's principle, into a body of work on the physical constraints and limits on computation. And it's an attempt to merge that work with philosophical concerns about implementation. What does it take to implement a computation physically? And we wrote a whole book, which we're like finishing, making the last revisions to. So it's a great opportunity here to share some of this with you. And I will apply to the indeterminacy of computation, and I'll present our result about the indeterminacy of computation. So it's very relevant to the theme of the workshop. So the plan is to give you a little bit of background, a little bit of terminology, then give you our account of implementation, and also the kind of way of classifying accounts of implementation by the strength of the mapping that they use to map the physical states of the system to the computational states, so that hopefully we're clear on what our account is. But then this is not shown here. There's also the application to indeterminacy. question, the indeterminacy issue. Okay, so this is the way I usually classify existing accounts of implementation. There's simple mapping accounts. There's restricted mapping accounts where the mapping from the physical to the computational is restricted by some kind of criteria, such as, it has the state transit, the physical state transitions have to, that map onto the computational ones have to respect counterfactuals, or they have to have the right kind of causal relation and so forth. Then there's semantic accounts where, in addition to whatever mapping there might be, the physical states have to be representations or some kind of representation, or maybe there are transitions between states that have to respect some of the semantic properties of the representations. And then there's mechanistic accounts where there's some kind of mechanistic structure that has to be present in a physical system to implement a computation. And as you probably know, I've defended a mechanistic account before, and now I'm taking kind of a step back, or like trying to dig deeper into, yes, but how does the physical really connect or bear the signature of a computation? Just to motivate, some accounts, well, mapping accounts as they've been formulated tend to lead either to unlimited pan-computationalism, where one and the same physical system implements many non-equivalent computations, or at least limited pan-computationalism, where everything computes something. That's an outcome that clashes with our, ordinary way of talking about physical computation, where we go to a store, and if we need a computer, we don't buy just anything. We don't buy a pail of water. We don't buy a rock. We buy this kind of thing, or maybe this kind of thing, but we wouldn't pay the same amount of money for a rock in a computer store. So the thing is that in trying to avoid these, other accounts might be too demanding, at least for some purposes. Semantic accounts require representation. Representation is definitely an important aspect of our computational practices, of the reason why we build computers. But it doesn't seem to be a necessary condition for a physical system to implement a computation. Even mechanistic accounts require all this mechanistic structure. Maybe sometimes that's not needed or necessary to implement a computation. There are a whole bunch of unconventional computing methods that may involve more or less mechanistic structure. I don't know if you're familiar with reservoir computing. I am not, but Neil is. So this is one of the many places where he and I collectively know things that at least one of us doesn't really fully know. And I don't, so even though I don't really know much about reservoir computing, he tells me it's a technique where people basically send signals to some kind of very complex system and receive outputs, and they massage the system in such a way that the input-output relationship corresponds to the arguments and values of a function that that they want to compute the values for, but they don't really know how the system works internally. So there's not that much of a mechanistic structure, or at least not known. And that's as much as I know about reservoir computing. The point is that there seems to be something missing from our accounts of computation, and here I'm going to tell you what that is. So this is just terminology now. We're going to talk in terms of physical systems. A physical system is a physical computing system, just in case it implements some computing systems. Yeah, so there's a physical system is a computing system. The physical system may or may not implement the computing system. If it does, then it's a physical computing system. And to do that, it needs to satisfy a sufficiently strong computational description. Obviously, this computational description is something that captures some aspect of that physical system. And so we're going to be talking about these computational descriptions and their properties. Okay, so another way to put it is that a physical system implements a computation if it implements a computing system that supports that computation. That's just terminology. And so now we can talk a little bit about types of description. So where do we distinguish between we might want to call them like non-computational, physical descriptions of a physical system, and those are just your standard models that you develop in your ordinary science. Okay, so you can even take the form of a computational model of a system, but it's not by itself attributing computations to that system. Okay, so it might be a system of differential equations. That's the kind of a standard type of physical description. It's going to have some physical state variables and laws that drive the evolution of the variables. Okay, so that's your normal physical description. There's nothing especially computational about that. Then you have computational definitions of the computing system. We call it a definition to highlight that in this case, we really mean to start with a computational formalism, like Turing machines, finite state automata. Doesn't have to be digital. It could be, the formalisms behind the general purpose analog computer, for example. So in this case, it doesn't just have ordinary states. It has these, it has the states, but it also has inputs and outputs that are distinguished so that we can say, okay, this is the input to the system, then it undergoes this process, then there are these outputs. And in a digital form, typically there's transition rules, transition rules from an input and an internal state to a output and another internal state, or sometimes it's just from internal state to internal state. So now you have these two descriptions. One depends on an existing concrete physical system. You're trying to describe some kind of concrete system. One, you can sort of make it up as you wish. You have, say, a Turing machine formalism, and you design your own Turing machine. It doesn't have, it's not necessarily implemented anywhere. So you're defining it yourself. Okay. And now you ask yourself, okay, under what conditions does a physical system implement this computing system? There has to be a mapping from the physical to the computational. And for starters, you have to map onto every element of a computational description for that to be, a candidate implementation, meaning all the states, all the inputs, and all the outputs, meaning for each input, output, and state variable, and each value of that variable, there has to be some physical state that maps onto that, or some physical force. In the case of an input, it could be a force applied to the physical system and maps onto an input. Okay, so all the elements have to be mapped onto. If you leave some out, then you're not even in the right business of implementing that system. All right, so this is the picture. The same thing in pictures. You have your computational formalism that from which you derive a definition of a computing system. And so you can, once you do that, you have your computing system. This is kind of basically just another way of talking about a computational description. What does it describe? It's a abstractly defined system. Doesn't have to be implemented anywhere. But on the other side, you have a physical theory from which you can draw a model of a physical system. This is a actual physical system that you're trying to describe. And within that, from some of the states in that system, not all of them, if you can draw a mapping of a certain sort, a sufficiently strong mapping to all the elements. So this is only some of the physical states. This is all the states, inputs and outputs. Then you're describing both the physical system as a whole, but also the states which at certain specific times implement the computing system. So again, there's only some states at certain select times that map onto all the states and transitions of the computation or any computation that's supported by that computing system. Okay, that's just the picture. And now I can tell you about our criteria for these mappings. Okay, so these two are what we consider to be uncontroversially needed for anything that aspires to be an implementation. Okay, so criterion S, criterion P. Then we're going to get to the one that is really the innovation, if you will. Before I say more, though, I want to stress that just like I said, that there has to be a physical state that maps onto every element of a computational description for that to be a candidate implementation. We require that also the number of variables, the number of state variables, input variables, and output variables in the computational description be respected, and the arity of these variables be respected by the mapping. That means, if you've got your Turing machine tape, for example, and there's all these different squares, you need one variable for the state of each square. You can't just lump it all together and call it like the global total state of the Turing machine, the state. So, okay, of course, the Turing machine has an internal state and the state of the tape. You could call that all one state, and give it a label and say it's a state 172. But that's not good enough to implement a Turing machine. You can't just take a physical state, a global physical state of a physical system, and say, oh, it maps onto state 172. You need to break it down and say, this substate maps onto the state of this square of the machine. This substate, distinct from the first one, maps onto this other square of the Turing machine, and so on and so forth. So you respect the number of variables in your computational description and the arity of the variables, how many possible values it takes. Okay, so that is a restriction that's not on the slide. And you also need to take into account the whole dynamics of the system, meaning, if your computing system has a whole state space, all of that has to be included, not just one run of the system. Okay, so at this point, this is something that I already said. It's sort of just restated more carefully. The state criterion is that there should be a physical state or force in the case of possible inputs that maps onto every computational state, input and output in the computational description of the system. That's the state criterion. So you don't leave anything out of that computing system. And for process, once you do that mapping from states to state, from some physical states, not all the physical states, some physical state to every computational state, then once you're in a physical state that maps onto one computational state, physically transitioning to a successor's physical state that also maps onto a computational state, it has to be transitioning to the right physical state, the physical state that maps onto the successor computational state. So the physical state transitions have to also map onto the computational state transitions. And that ensures that the physical state transitions, and therefore the physical states, incorporate at least as much information about the computational evolution of the computing system as the computational states in your computational description. Okay, so basically you can reconstruct from the physical state transitions, you can reconstruct the computational history of that system, past and future, to the degree that you can from the computational description, or possibly more. And that is the important point, that our next criterion, which we call physical computational equivalence, states that there shouldn't be more information in the physical states about the computational trajectory than there is in the computational states. This is a, as I understand it, this is basically a direct application and generalization of Landauer's principle. Landauer's principle says that that erasing information within a physical system has a physical cost, meaning it takes work, it takes physical work to erase information. Typical computations are irreversible because you have to erase some information, meaning, for example, that there's more to this than Landauer's principle, but this is one of the ideas behind it, okay? And if you're familiar with Landauer's principle, maybe this is a way to motivate it. There's a lot more, and we go into all of that in the book, but I can't go into all of it now. But if you think that typical computations are irreversible, one reason, or the main reason they're irreversible, is because multiple predecessor states merge into the same successor state. And I can show you a picture here. So there's a finite state automaton. From both C0 and C1, you can go to C2 under the same input I sub 1. Okay, so two different states lead to the same successor. Once you're here computationally, you no longer know whether you came from here or you came from here. It's all the same at this point once you're here. So PCE, principle of computation equivalence, says when you try to implement that, and this maps onto C, what was it, 1 or 0? 0. Okay, this maps onto C0, this maps onto C1. This is a class of physical microstates. And then they can both converge onto the same class of physical microstates that map onto the C2. Okay, yeah, it looks like this is all good, because you have two predecessors that merge into the same, successor state, but PCE is not going to be respected unless once you are in these microstates, you're no longer able to retrodict or infer which of these you came from. Okay, so this picture alone doesn't tell you whether physical computational equivalence is respected, because it's possible in principle that you could go from here, even though you're lumping this together. I mean, just because you draw an oval around this state of microstate doesn't mean that there's no information here about whether it came from here or from here. If there is this information, you're not respecting physical computational equivalence. If that information is lost, once you enter this kind of subspace, you lose this information about where you came from, then you respect physical computational equivalence. That's the idea. Hopefully that makes sense. Okay, so that's physical computational equivalence. There's one other criterion that we could require. We don't require it. It's usability, and it's basically the existence of some kind of protocol for interacting with the system, such that you can set it up on an initial state of your choosing, and then you run it, and then it gives you the value for that argument of the function that you chose, so that you get the system to do the computational work that you want when you want it. Okay, so obviously that's convenient. Obviously, digital computers satisfy criterion U. They also satisfy PCE. But for these purposes, we're not requiring U. We're leaving that as an additional thing that is nice to have when you have it. But there's something special about PCE, and so that's the kind of the basic focus of this book. And so what we say is that to get a sufficiently strong mapping between a physical system and a computing system, to the point that you really genuinely implement a computation, you need a robust computational description of physical system, meaning that it satisfies SP and PCE, not necessarily U. Whereas if you only satisfy SMP, in a very weak sense, you have a computational description of a physical system, but it's not a genuine implementation in the sense that, that physical system, if, under those descriptions, if it doesn't satisfy PC, then it doesn't bear the physical signature of that computation or of that computing system. And of course, you can still have a strong computational description, in which case you also satisfy U. Okay, so our iPhones, our laptops, they satisfy strong computational descriptions, but a robust one's enough to implement in a important sense, okay, to bear the physical signature of the system. And I mean, it might be exotic applications that require only a robust computational description of a physical system as opposed to a strong one. But still, there's something important about it. That's why we're stressing that. Okay, so there's objective reasons to put a description into one of these classes, but clearly there's something subjective about saying which one is the one that's good enough or strong enough. But we do think there are very good reasons to pick this one as opposed to a weaker one. And here we have a nice little flow chart for how to assess all of this. I don't think we need to go through this in any detail. It's sort of another way to summarize what I said. But basically, you can start with a putative implementation. Somebody says, oh, this physical system implements this computing system. And then you ask yourself, do we have physical, a description of physical system and a computational description or definition of the computing system, and do we have a mapping from the one to the other? If not, you're out of business. If yes, then you can ask, is S satisfied? If no, never mind. If yes, do you satisfy P? And you keep going, and then you get to either a weak or robust or strong computational description with the right kind of mapping, or you might end up saying, no, that's not a genuine implementation. So the robust mapping account is a way of saying kind of what I just said, which is that if it's a weak mapping, it's insufficiently strong. And in order to implement a computing system in a robust way, genuinely, you need to bear the physical signature of that computation or the computing system. We use computation for like a run of the computing system, and then the computing system for the whole system with all its possible inputs and processes. But the point applies either way. So what it takes for a robust implementation for bearing the physical signature of a computation is satisfying physical computational equivalence, and that's what ensures the full mirroring of the computation in the physical. So that's what it takes. The strong ones that also have usability are more than enough, so they're not required. So again, you're going to implement a computing system if your physical system satisfies a physical description that maps at least robustly onto a computing system, which is described by this type of computational description. And at this point that we have the robust mapping account, I think, yes, I can say a little bit about the indeterminacy of computation. And this is I think a nice result that comes out of this account. And that is that in this kind of case, which is due to Iran, Shagrir, there isn't really as much indeterminacy as we might have thought. So I'm going to point out that in this kind of example, only one of these computational descriptions is really robustly implemented, okay? So just as a reminder, this example, I think came out initially in a paper from 2001 that Ron published. And I've thought a lot about it over the years, and I didn't realize what I'm going to tell you now until Neil pointed it out. So I have to give him credit, my co-author. This is a tri-stable system. It has three possible states. We'll here label 0, 0.5, and 1. And this is the table of inputs, input pairs. It's kind of like a logic gate, but it has three possible states. So if the inputs are 0 and 0, the output is 0. If it's 1, 1, the output 1. Otherwise, it's 0.5. But you can lump together two of those states, and here we lump together the 0 and 0.5 and call those 0. And if you do that, you get an AND gate. Because now, still, if the input is 1 and 1, the output is 1. But otherwise, the output is always 0. So that's an AND gate. I mean, with some duplication in this table, because I was just repeating all the lines of the original one. But you can do the lumping differently, and you get an OR gate. I'm guessing most of you are familiar with this. So this is the exact same table from before, but now we lump together the 0.5 and the 1 and call that a 1. So now, if the input is 0 and 0, you get 0 as an output. Otherwise, you get a 1. And so this is an OR gate just from lumping together two of the three possible states in two different ways. And one of the things that's been, people have been writing about is, okay, so what do we do about this indeterminacy? This is one and the same physical system. But depending on how how we label it, or how we map the physical states onto computational states, meaning these are basically computation descriptions, and we have three of them. We have this one, the original one, we have the OR one, and we have the AND one. Well, it looks like there's different functions that are computed, or at least computationally ascribed to the system. So what do we do about this? Do we need representations? Do we need semantics? And the answer is no, we need a robust mapping account so that we can show that only the original one is robustly implemented and the other ones are not. Now, we can still do the labeling, and we can still maybe have some value for us. We can lump these things together, but the work is done by us when we do the lumping, not by the physical system. The physical system is doing this computational work in a robust way. And all you need to do to see this is that you imagine that these are physical macro states that are labeled this way. By assumption, these are going to be robustly implemented, this one. Otherwise, we're not even in this conversation. So we're going to assume that these are robustly implemented. If these are robustly implemented, then these are not. And the reason they're not is that here, once you do this lumping, you cannot distinguish anymore between whether your input was 1 and 1, or it was something else, something different. But here you can, when it was 1 and 1, whatever states, these are, I'm mapping onto the 1 and 1, it could be some voltages. Here you can distinguish between this possible input and these possible inputs, but here you can't. And same thing with the AND. You can you have this information here between whether your inputs were 0 and 0 and something else that wasn't 0 and 0. but here you have lost it, but you haven't lost it by erasing information, you have lost it physically, but you have lost it by just doing the regrouping of the states. So anyway, that's just to say that the indeterminacy is only apparent with respect to a robust mapping account, because only one of the descriptions is really implemented robustly and the other ones are not. So conclusions, I didn't go into all of this, but the robust mapping account is an attempt to capture the physical signature of computation. It rules out Payne computations on principle ground. We do discuss that a lot in the book. We go into a lot of different types of Payne computationalism. It accommodates, unconventional models of computation. It can be generalized beyond digital computation. It applies to both natural systems and artifacts. We do have a chapter on the brain and the mind, where we talk a little bit about this. And it's consistent with other richer accounts like the mechanistic and semantic accounts. And it can be simply added as a condition within other accounts. So we're not saying that you shouldn't have usability, or you shouldn't have mechanistic structure, or you shouldn't have representations, or representations don't matter. It's just that we're saying we also need physical computational equivalence within any adequate account of implementation. And maybe for different purposes, we might require stronger notion of implementation than the one that just has physical computational equivalence, plus, of course, the two other criteria, S and P. I just want to add that it seems to me that when it comes to semantic accounts, they are right that representation is important, that representation is deeply connected with computation. And this is especially true when it comes to the brain and the mind. And I have come to appreciate this more and more over the years. But still, representation is not a necessary condition for physical computation. What is a necessary condition is physical computational equivalence, in addition to S and P, and some of the other things that I mentioned briefly. So the way I see it now is that semantic accounts are almost correct in an important sense, because they tend to focus on the mind and the brain. And when it comes to the mind and the brain, computation and representation are two sides of the same coin, meaning it's the system itself that builds its own representational system by processing inputs and responding to them, or responding to the world, if you will. And I don't think we fully understand how that even works, but we are starting to have some tools for understanding that. So the system has to either be set up through evolution and development, or maybe learn. There's going to be a lot of learning involved to build its own computations and representations at the same time. So as it builds the representational structure, it also builds the processes for activating these internal states, these internal representations, and using them and acting on them. And that's why these are what I would call, among many others, original representations, with original semantic content, or if they're intentional state, they have original intentionality as opposed to derivative intentionality. Whereas these machines, in the first instance, they have derivative intentionality, and their semantic properties are not as deeply connected with the computations. The coordination, so there's coordination between the computations in these systems and the content of the representations when they are representational states, but that coordination is largely established by the designers and programmers of the system, at least in the first instance. I mean, of course, these systems can also learn, and that can happen eventually, but the machine itself, the machine code of the computer, it works because it's designed to work in such a way as to respect the semantic properties of the representational states. It didn't learn on its own. It didn't build that connection or that coordination on its own, but the brain does have to build that on its own. So there's an important difference, and this kind of difference is important also to study, to think about. So that's something we should be thinking about and understanding, as well as we can. And so, there is a sense in which for the brain, a semantic account is correct or almost correct, meaning the computations and the representations are intertwined. The computations are part of what builds up these internal representations and then uses them. And the representations are what makes these computations work, because they are getting the organism to behave successfully in the world on the basis of these representations. Okay, but still with all that being the case, the physical signature of the computation has to do with physical computational equivalence, and has to do with the physical states containing the same information as the computational states with respect to the computational trajectory of the system, neither more nor less information. Okay, so that's our story. There's going to be a book about this. Yeah, if you want a copy, I can send it to you soon. When we're done this. Yes.
So it seems that this equivalence depends on your measurement device, the physical system. If we go back to the original example, also to look at this example, you go back. Yeah.
So here.
Yeah. So if I'm able to measure all of the three states, and you'd say that it's not let's say that my measurement device, I'm measuring this physical system, and I cannot distinguish between 0 and 0.5. And I get different results if someone that can distinguish between 0 and 0.5 and does this something later.
Yeah, good. Thank you. That's a good, interesting question. It's definitely not supposed to depend on our measuring devices. So there's going to be questions about how we find out that this is how the system works, and that can be challenging, of course. But this is supposed to be, physical computational equivalence is supposed to be an objective property of the system, and it's easier to discuss when it comes to these artifacts that we understand fairly well than when it comes to brains where we didn't build them ourselves. But when it comes to these devices, one of the tricks of computer engineers, I am told, I don't really know this stuff, is that there might still be it might still be possible to distinguish where a microstate that belongs to a certain computational state was coming from. Was it coming from a 1, or was it coming from a 0, as a predecessor? But only for an infinitesimal amount of time. Once the clock signal arrives and the system is supposed to update, and so we're going into a new computational state, there's a sort of randomization of the microstates, which very, very quickly makes it impossible, no matter how precise your measurement is, to infer what the predecessor was. And this is, I guess, this is what I'm told, is due to interaction with the thermal environment of the memory cell. So a memory cell, has a thermal environment. It's sort of juggled by its thermal environment. In the microstates, there are still billions of possible microstates. And in theory, you could try to divide them into those that came from one predecessor and those that came from another predecessor, but they basically get quickly mixed in a way that makes reconstructing the history impossible. So in this case, it is an objective feature of the system that it's not possible to extract any more information about what was the predecessor from the physical microstates than it is from the computational state that those physical microstates map onto. So that's the gold standard that we're proposing as the requirement for a robust implementation. I hope that makes sense.
So it's a microscopic level physical rules are in principle reversible.
Well, they are in principle reversible if you have if you can consider either a closed system or the whole universe. But in practice, when you have a physical system like the kind that would normally be considered a computing system, there is an environment. So there is a boundary between the system itself and the environment. There's an interaction with the environment, and that interaction ends up erasing information in a way that contributes to a robust implementation or a physical computational equivalence. Anyway, that's a very important key point, and you're right to ask about that. So yeah, this is one of the things we talk about in the book, and it's a distinction between kind of idealized physical systems, where you just have your neat theory and you say, oh yeah, the universe, like the laws are reversible, and when you're doing something closer to engineering of mid-size objects where you have to deal with the boundary between the system and the environment. Yeah.
Maybe to continue the previous comment. So if I understand correctly, the crux of your new idea is the physical computation equivalence. So you have these other principles, the state principle, the process principle, but those are well known. So that's the new thing. And it builds on something about Landau's principle. My worry is that among philosophers of physics, it is already acknowledged and quite well known that this principle is mistaken. It is not a theorem of physics. That's already acknowledged. And we have shown, Meir and I, in a paper just maybe 2 or 3 years ago, that there is that the counterpart of Landau's principle and the fact that it is not a theorem, the counterpart is the multiple computational problem, the individuation problem that we will discuss today. So those are basically in physics the same problems in different words, and we illustrated this equivalence of these two principles based on Oron's example that we now see on the slide. So the thing that is the fact that is already acknowledged, that I say in among philosophers of physics with respect to Landau's principle, is that this principle is based on a preference for a certain description of the microstates, as you've just commented. And the question is one of principle. Namely, we're not interested here in, if I understand correctly, in engineering difficulties, important as they may be for building computers. That's not the question. The question is one of principle. And the principle is that Landau's principle, as well as the problem of multiple computations, are about the way that we as agents or creatures with minds or whatever see the world. The way that we partition the state space into macrostates. This partition is not out there. It is brought about by us and by our measuring devices. And this is the point that brings about the problem as you nicely described it here. And the same thing is said about Landauer's principle. Landauer's principle, I mean, the way that Landauer's principle is phrased sounds mysterious because it draws a very close connection between the physics, the thermodynamics, the entropy, and the logic. Logic and entropy seem to be counterparts. This seeming equivalence between logical properties, logical irreversibility and entropic irreversibility, is only a result of giving objective status to partitions that in fact are a result of the way that we look at the world. To some, sorry for this lengthy comment, Landauer's principle is not a theorem of physics. And you cannot rely on it in order to solve the indeterminacy of computation problems, because those are counterparts and they stem from the same epistemic view with respect to macrostates.
Your turn.
Thank you, Arlie. That was very very rich question. I'm gonna try to say three things if I can remember all of them. First of all, the physical computational equivalence principle is not motivated only by Landauer's principle. And I mentioned Landauer's principle only as a way of referring to something that if some of you might be familiar with as a possible motivational route. But another motivation that I'll briefly mention is that if you from some physical descriptions, it might be possible to reconstruct out of multiple times. So a computational system could go through, say, like a sequence of states, A, B, A, B, A, B, multiple times. It could like oscillate between different, the same two states. If you have a physical description, you could be able to reconstruct if this is the first A or the third A or the seventh A that you're visiting in your evolution, dynamical evolution. But if you have a computational description, you can't. You just know you're in state A or in state B. So PCE says you should be able to infer, which of these you're in from your physical description if the computation is robustly implemented. It should carry the same amount of information about the computation evolution. I mean, yeah, that is if you will, that's an intuition about what constitutes a robust implementation. That there's no physical law that says it has to be that way. It's just that there's at least plausible reasons to go for that kind of restriction on implementation. That's point one. Point two is that Landauer's principle is controversial. You made it sound like everybody knows Landauer's principle is wrong, but in fact, there are people who think it's correct, or basically correct. And Neil Anderson is one of those people, and he's the one who really has published in this area. What did you say?
It's a mistake.
Right. So so he might be mistaken, but he has published recent work, trying to address the philosophical concerns with Landauer's principle. And so he really need to be here to address that, because that's like above my pay grade. And also we don't go into it in the book. You know, we give references to some of this literature, including his recent work. But we don't really get into the dispute over Landauer's principle. But he's very confident that there's an important respect in which Landauer's principle is correct. So I'm gonna refer you back to him. If you want to send me more papers by you on this, we're still finishing up the book. There's still room for adding references and possibly fine tuning things. We're not going to give up on Landauer's principle ourselves, but we can like, you know, add references or maybe more discussion. I don't know. And the third thing is that regardless of exactly how we come down on Landauer's principle, this is not just a mere matter of engineering difficulties. It's supposed to be, you know, the aim is to capture something objective about these kinds of systems. So yes, there are mid-sized systems. Yes, there's a sense in which the boundary between the system and its environment is something that we draw. But even so, it still captures something objective about how these systems work, that once you update the value of a cell, of a memory cell, and you know, you have your charges floating around the capacitor, you lose the information within that cell. So within that, you know, space that you select and you say, okay, this is the space that I'm looking at. In there, the information about what the predecessor was is lost. Yes, it might be somewhere in the environment. That information might still be preserved somewhere in the thermal environment of that memory cell. And you might want to say, oh, well, it's just a mere technological difficulty that you cannot find it anymore. But it's sufficiently important that, you know, this is the machines that we use. We know we don't use the thermal environment of the memory cell to figure out what the computation is that's being performed. We use the value of the memory cell. So, you know, it is an objective feature of the memory cell. And that is important to us as users of these machines, or you know, and whatever project we might have that has to do with trying to understand what physical implementation of a computation is in a mid-size object. If you want to go and talk about computation, you know, in fundamental physics, there's other considerations that become relevant, and we have a chapter on that, you know, on ontic and computationalism. That's sort of a different beast, but yes, this work is motivated to a large degree by trying to understand objective features of mid-sized objects where there's an important distinction between the system itself and its environment, and the environment is a sort of heat bath, and it can't really be sorted out anymore, like where the information is. So yes, if you want to call that subjective, that's fine, but it's objective enough for many of our practical purposes.
So we've got at least 4 more questions that I've recorded. That's before my 3 questions, and in like 5 minutes we're starting eating into the coffee break. So we'll try to keep it brief. Mayor first, then Paula.
So I just wanted to maybe sharpen a little bit the point about Landauer. I'm not sure everyone understood here. And that is that, I mean, we're not saying, I mean, Landauer's principle is a special case. So if you look at the behavior of the physical system, then for some special cases in which there is a certain relation between the dynamics, the dynamics of the system and the way you group the microstates or the macro states as they occur. For some, if a certain relation holds in these cases, then Lando's principle will hold. So it's not a general case. This is what Oli was talking about. So if you want to put a general condition on the computational and physical equivalence, and you require that Lando's principle be satisfied, then your condition is not going to be general. This is something that I think we can understand, and that's and so that's one point. The other point, I'll be very brief. I just wanted to ask you something. It seemed to me that when you were describing Ron's example, you've treated the grouping of the states as if it is something that is sort of subjective or something that is imposed by us on the system. But I think that this is not the right way to look at it, because all these groupings basically reflect some physical properties of the system. And all of them are equivalent in this sense. Some groupings are more useful to us, some are less useful. You know, it's a question of so this is like I just wanted to understand your take about the groupings. Do you think about them as something imposed by us, which has nothing to do with the system, or do you accept the idea that they are actually these groupings are basically macro states? That's what they are. So they are there, objective, even though we may not be able to measure them or something like that, but that's there.
Yes, thank you. Well, they are there, but this is kind of a conditional argument. If the first kind of grouping is robustly implemented, then the second type is not. Of course, it could be not, it could be that none of them are robustly implemented, then we don't have to, we're not in this kind of argument anymore. So not all microstates are the same or equally, carve the system at its joints. So, if the first kind of groupings carve the system at its joints in the sense of, is robustly implemented, then the second one is not. That's the claim. So, I mean, I didn't even expect it to be the case. We rewrote that whole section of the book because we had a whole other discussion of it, and then you'll notice that this is the case. So it was kind of a breakthrough for us.
Yeah, so I have two clarification questions. So when you were presenting your levels of description of computing, like weak, robust, and strong would be robust and weak. So you gave the example of a PC, right, as a strong implementation or strong description of implementation and relation mapping between the computing and the physical system. But then when you were referring to the robust level, well, you gave this example, I get it, then you spoke about mid-size objects, right? But I would like it concrete, like here I understand what is the high level, but robust and weak, I feel like I cannot yet make a connection to the real world. Could you give some like concrete examples? So this is my first question. And the second, I didn't really understand your concept of derivative intentionality. So if you could say just like a few words more.
Yeah. So I have to be brief. So weak, an example of a very, very weak description. There's a bunch of classic examples of constructions in this literature. There's Putnam's rock, and it's just a rock, and it kind of gets heated by the sun or something like that. And he says, well, take it a state at a certain time, and then a minute later, it goes through different states, and you label those states as computational states. Oh, there, boom, it has an implementation. So that's a very weak computational description. The mapping is weak. It's definitely not robust.
Will there be something that doesn't compute at all in this situation? That's a computing position.
Well, we want to say that it's not computing, at least not computing what Putnam says. And then there's like
A robust then.
there's more there's more interesting cases, like there's Chalmers clock and dial system. It has a clock and a dial, so it can take these different states and it goes through a sequence of states. That's still weak. Robust would be maybe a reservoir computing system where before you really figure out how to use it, you might still want to say, well, that was already implementing a computation. I don't know how to use that, but there was already this kind of mapping or this kind of structure between the physical states and the computational states. But yes, the standard kind of paradigmatic cases are cases where there's also usability. And you also, you asked about
Yeah,
derivative.
yeah,
That's where, you have a word, and that word means something to those who know the language of that word, in which it's written. But, to somebody who doesn't speak English, they come here, that doesn't mean anything. So it doesn't really have any kind of intrinsic meaning of its own, its meaning or content, meta content or intentionality that is derives from the fact that there's a community of users who know how to use that word.
and you were referring the derivative intentionality to the indeterminacy of computation, right? Because I just missed that somehow.
Oh,
I stopped following you,
No,
and then I heard this
I was talking,
expression that is attractive to me, and then I
Yeah.
said, but
Well,
what did he mean? What did
maybe
he
we can
mean?
talk about it, line shifts.
Great.
It's a long conversation.
Since the example is yours. Go ahead.
Just, it seems that your claim against the indeterminacy, I mean, if you can.
Here,
Yeah, I mean, it seems that your claim is not just conditional, it's also relative. You say this is not robust, given that this is robust. But we could say, well, from the beginning, forget about this, and this is robust. Now what? Because also for this, you can say, well, maybe, there is 0.4501 and 0.498, and to do, and then there is some robust mapping, and then this is no longer robust relative to the more basic robust. So, so you see there.
I
So
think
your
I
notion of
understand the question.
robust is relative, and I think it goes back to all the questions about measurements and.
You're saying what, so can we stipulate, this is robustly
Not
implemented,
stipulate,
then,
this is, I mean, forget about this. You have, from the beginning, right, you have 0 and 0.5, right? Goes to, in this case, to 0 and 0.5, right? And 1 and 1 goes to 1. And under this description, it is robust. Why not? If you say it is not robust, I mean, it is not robust only given, I think, that you already decided that this is robust. But then I can come and say, but look, if I also can build something that you have like a more robust mapping of this system. Let's say that there is more robust mapping. It has to do not with 0.5, but with 0.497 and 0.501. And there is some robust mapping there. Relative to this more basic robust mapping, this will not be robust, much like this is not robust. So, or I missed something in your
still trying to
definition.
understand you.
Okay.
Are you saying, let's suppose that this is robustly implemented. What can we say about that mapping? Would that be not robust then?
I don't see why this one,
Yeah.
right, is not robust.
So this is not robustly implemented because the physical states are such that once you lump them together, you're not supposed to be able to distinguish between this kind of input and this kind of input. But if you look at the physical states themselves, on the assumption that that is robustly implemented, you
No,
can.
don't assume this.
Well, right, like, that's sort of the
Well, this
more
is the
fine
basic
grained.
assembly.
Yeah, the more fine
Yeah,
grained description.
but that's my point, that maybe there is a more fine grained description
Yeah, but
than
it-
this,
so if
and then
this
this
is-
will not be robust.
But if this is robustly implemented, it means that once you're in this kind of physical state, like
Yeah.
voltage 7 or whatever
Right.
it is, or voltage like 4 to 7,
Right,
any of those. Whichever one you're in, you wouldn't be able to, to reconstruct whether the inputs were either like, between 6 and 7 and 6 and 7, the input voltages, or one it was between 6 and 7, but the other one wasn't. It was maybe like between 4 and 5 volts. So, so you wouldn't be able to do this, and you wouldn't be able to map this onto the system if this is robustly implemented.
yeah, but they
Like that
don't.
would not be,
But
that
they
would
don't,
not work.
because the microstate is, one microstate is between 0, 5 and 1, and the
Yeah.
other is between, let's say, 0 and 5, that's it. So you don't have to, these are the macrostates.
Yeah,
Okay,
let's
let's
get
discuss.
Okay, they can continue, they can continue.
So one last
Yes.
question, but Andre, we'll keep it very brief and break for coffee.
Yes, really brief, because I don't want to stay. So I guess I'm wondering about, I'm still sort of bugging me. So the definition of a physical computing system is, a system, the physical computing system, just in case, implements some mathematically characterized computing system. I guess I'm still wondering how you're characterizing the mathematically characterized computing system. So what makes something, on that side of computation? And the sort of the worry that I have is that it's not entirely clear to me how to see how you're going to do that without dealing with sort of pragmatic factors, or something like these are the kinds of things that computer scientists worry about or use in their practice. So yeah, I guess I'm just wondering what sort of more principled thing there is to say on about the right hand side of it.
Good, yeah, right. It's a good question, and where we've landed with this is that there should be a clearly specified in the standard case, and you can always, make modifications, but there should be a explicitly defined mathematical quote unquote problem. This is potentially a general problem with uncountably many instances. And a process for generating the solutions to the problem, each individual solution. So, or you can call it a function from an argument of value, or you can call it input and output, and a way of going from the inputs and the outputs. But I think problem is helpful because it highlights that you're trying to find something, and there's gonna be a method, algorithm in a broad sense for finding it. This is not generally how we characterize physical systems in general. We don't think of a rock as solving a problem. We find it, and when we ask, like, what is this and how does this work, how does it do what it does? But when we try to do computation, it's because we're trying to solve a problem, or even better, solve all the instances of the problem, with many, with countably many instances. So that's the idea. So it doesn't have to be a digital formalism, but it has to be something that solves a problem in a systematic way. That makes sense.
Okay, let's think what we are reading.
Okay, we will move to the second session. Yeah, I forgot to mention in my introductory remarks the most important one, and that is that people from the Institute told me not to fix coffee in the middle of the lecture because the machine is very noisy. So this is the okay. And now I'm very pleased to present Paula Tinon, and Paula is from Lund, but also from the Warsaw University of Technology, right? And Paula will talk about the variety of computation in the framework of Carnapian explication and in conceptual spaces. Wonderful title, and we are looking forward to it.
Thanks so much. Well, Oron, thanks for inviting me because I wouldn't be here if you, Nir and Oron have not organized this wonderful gathering. It's really awesome to see so many familiar faces and people I have not met yet. So for those who went already to other workshops on computing that we attended this summer, you saw part of the presentation that I'm giving here. But I did improvements, so it's a new presentation almost entirely. So conceptual spaces are not very popular with this crowd, and I started using them. So this is like a little bit of a coming out because I get money from the Polish National Science Center to work on a representation of the concept of natural number. In conceptual spaces. I will explain you briefly what are conceptual spaces. I will not go deep into this framework because like for me, it was a side project, but now I think that it was a very good coincidence because I enjoy working with concepts, right? So this is what I do. This is what drives me. And this is how I understand my role of a philosopher is to play with concepts, right? And the concept of computing and the concept of number, as I'm going to tell you, are very strongly connected for me. And yes, and this conceptual spaces framework is very handy when it comes to work, even with those abstract concepts. Okay, so what I was thinking of and why I started this project is that this computation has very different meanings. And I come from a very theoretical background, which means that when I was thinking about what does it mean to compute, I was trying to understand what does it mean to compute with a Turing machine? What is the domain of computing, right? Is it natural numbers? Are those inscriptions? Can we have a concept of computing without a domain, right? Maybe that would be possible as well. So those are the questions that were driving me from the very beginning. And with time passing and me organizing workshops, going to workshops, talking to people, I discovered that this is just one, maybe now, very narrow understanding of what computing means, right? There's a lot of things to do over there, but then you have all this crowd of people interested in physical computing, cognitive science, brain as a computer, etc. And they are having intuitions, so you are having intuitions, and you're using competently the expression computation, right? So I started to write this book, which at first was supposed to be devoted to intentional differences between models of computation, right? So here we speak about Turing machines, recursive functions, lambda calculus, right? Everything on this classical 30s studies of what is computing, right? And there's a lot of problems there, right? And now I decided, so this part of this talk will be partially devoted to my incompetences in all this area, which are related to semantic computing, physical computing, analog computing, and all those other like uses of the expression computation that I think belong to the book about what computing means, right? So I hope that you can join me in this journey, learn something from it, but I really hope to learn something from you as well. So as I said, my starting point was computational analysis. My PhD was devoted to the argument from Tenenbaum's theorem. So I was trying to justify that there is a very adequate way of defining what natural numbers are when you can prove or you can justify that your domain can be used for computation. And that was in the context of non-standard models of arithmetic. And I won't be speaking about non-standard models of arithmetic here because that would take too much time and it's not completely relevant to what I want to say. But I landed at the idea that computation is strongly entangled with discrete domains, right? So instead of speaking of natural numbers, I wanted to speak about, like you can just always have a next one and it goes into at least potential infinity, but there's probably also the actual infinity of those objects. But the study showed me as well that there is an intrinsic vicious circle in these investigations, and that I cannot I cannot ever go out of it. I will be always model. I will always have to relate to some like concrete model that I don't know what is this model because I cannot distinguish that in the language, etc. So I found this work extremely frustrating. And then at some point I discovered that Carnappian explications are sufficient enough for my level of OCD. You know, it's like, it's okay, right? I don't have to do analysis all the time. I can go Carnappian explication, and it provides me a framework that will be strict enough and well-defined enough for me to have a feeling that I understand something better and something more, and it doesn't keep me in this land of analysis, which I love and I belong to, but I want to make progress. So that was my way of thinking that I can make progress. So I started to look at Carnappian explications as applied to the concept of computing. And I have this paper in which I justify that Church-Turing thesis with an emphasis on church, right? Because it's mostly devoted to Church's approach, is a Carnappian explication. And I'm going to show you which steps you have to apply in order to justify it and which benefits you can get out of it. Then with Alessandro Facchini and Monaldo Mastrolilli, we have a manuscript, and I already promised that to many people, so I hope that by the end of the year we are really going to have a manuscript. We actually applied for a grant proposal, which got rejected, but like a lot of material is already there, and I already presented that several times. And this is a paper in which we apply the same methodology of Carnappian explications to Cobham-Edmond thesis, right? So I'm going to show you this Cobham-Edmond thesis explaining what is feasible, what is a feasible computation. Here, instead of digital, I might have said effective computations, and this feasible, it's a more narrow meaning of what effective means, right? Because we are putting time constraints of what is or what can computing means, right? And then my latest project, and this is where I hit the wall and made fool of myself at several talks. I wanted to get a similar analysis for analog computing, and then I couldn't. And it was frustrating, and the paper got rejected again, and we managed to present it several times with this collaborator. So it's a colleague from Warsaw. And it's a whole new journey that opened in front of me. And here I'm going to tell you some things about this analog computation thesis, about the work that we have done with Paweł, and also, you know, I will show you where is my ignorance, which is fun, right? There's a lot of things I control here, and there are things I don't know. This is what workshops are for. This is how I see that. Good. So Carnappian explication, just to give you, for those of you that are not that accustomed with this methodology. So Carnap, so that, you know, that comes, it's a whole tradition, right? It's not Carnap who formulated explications. It was in the Vienna circle, but also before, people were working around something that they call rational reconstruction, and they were trying to capture that in some way, that it could be used in different contexts, and it will be like, you know, like some kind of like homogeneous methodology. And Carnap in the 40s started to speak about those explications in his account, and in a book about probability in 1950, he devotes the whole chapter to the method of explication. And his method of explication consists, so he's very so he says that this is a transformation from an intuitive pre-scientific concept into a formal concept, right? So we have, from the one hand side, we have this inexact concept that we use on everyday basis, or even in some pre-scientific talks, but it's not like entirely formal. This is the explicandum, and it is transformed through the method of explication to a new concept, the explicatum, which belongs to some formal pre-existing theory in which we will be having this concept represented, right? It's a two-step methodology, so an extremely important step, which is very under studied in the literature. And I'm trying to make sure that people don't forget that really pay attention to the clarification step, right? So in a clarification step, through diverse examples, through discussions, through like approximations, you're making sure that the concept that you're going to specificate in the next stage will be clarified as well as possible. So Carnap himself gives the example of the Swiss knife. I really like this example. So you have a Swiss knife and you can do almost everything with that, right? If you have a fancy one, you can, fish and open your beer, and then you have screwdriver and the wine bottle opener, whatever. And I love those little drawings, so you will find it in my slides. So you will, through Carnapian explication, the Carnapian explication is like having this Swiss knife on a intuitive, pre-scientific side, and you're having concepts clarified and then explicated in the formal context. And so there need to exist a formal context. Maybe I was not sufficiently explicit about it. There need to be a formal context, and to this formal context, we are going to, in this formal context, we are going to identify which part corresponds to our intuitions. And well, I've made an attempt to draw a sushi knife, and that was supposed to be this tool that you can use to make very fancy decorations for your bedroom, right? Like in wood. So another important thing, we had a discussion with Andrea about it recently. Carnap believes that even if you introduce those formal concepts to your language, to your scientific language in different contexts, you still keep your intuitive concept at use, right? As you will always keep your Swiss knife in a pocket, right? You will not carry a saw if you go for a walk, right? So, and then, well, how can we make sure? So there is no criteria of how to formulate an explication except from those two steps that you need to execute. What happens is that afterwards, in order to compare in a given formal theory, we want to compare two competing explications, and then Carnap, he provides us with adequacy requirements on the specification, and those are quotations from Carnap, 1950, so the book on probability I told you about, and there are 4 of them. There is similarity, so it has to be similar to some extent to the intuitive concept. It has to be there has to be some kind of exactness, right? So it has to be well connected to other scientific concepts from the context we chose. It should be fruitful, which means that if you can, from your formal concept, deduce some general laws, right? And then you have this intuitive concept still there, right? You will learn something about the world as well, right? Like this intuitive everyday world. So this is what we want. And then it has to be as simple as possible, right? And those are not very formal requirements, but they are good enough. Good, and I have to speak quicker. Good, so Carnapian explications are claimed to be a form of conceptual engineering and can be modeled in conceptual spaces. There is this extremely nice paper by Matteo De Benedetto, in which he gives a Carnapian explication of Carnapian explications through conceptual spaces, and it's a very nice one. And this is what made me think that it is maybe a good tool to use those Carnappian explication, those conceptual spaces in the concept that I'm interested in, which is the concept of computing and the concept of number. So conceptual spaces, this is Peter Jerdenfors from Lund, who published 2 books about it and an infinite number of papers. When you think about conceptual spaces, you think about model of conceptual representations. I was asked about philosophical ontology of conceptual spaces. Please don't do that here because I won't have anything to reply. I just use it as a tool, right? It's a good question. I think it should be studied and it is understudied. But at the same time, I have nothing to say about it. The key tools in conceptual spaces, so information is organized in quality dimensions. So when you have a color domain, you will have a domain, like you can decide upon the brightness of your color, intensity, and the hue, right? And on this, in this figure inside, you can represent all colors there are by deciding that, for example, pink will be here, right? Those quality dimensions are endowed with a metric. So you can express how similar are objects in a conceptual space. Like for example, yellow here and the pink just next to it will be similar, and it will be more different than something which will be placed over there. And those quality dimensions are sorted into domains. So brightness, so those brightness, intensity, and hue are quality dimensions that belong to the domain of color, right? And we'll have domain of action, domain of numbers, domain of different domains. Most frequently, the concepts on the conceptual space are presented within a very nice tessellation. This is very convenient, especially that it is claimed and proven by people working in conceptual spaces that natural concepts are represented by convex regions, right? So if you have 2 concepts belonging to the same space, you can draw a straight line between them, right? It will be not like this kind of figures with something which is not in a space if there are 2 concepts on the same space, and it's obviously multi-dimensional. Well, I couldn't draw more than 3-dimensional. And there is a theory of prototypes, which is on top of the conceptual spaces, which means that every concept has a prototypical concept, which is kind of like a representation. Like, when you think of the concept of a dog, the prototypical dog will be different for me and different for some of you. I am for pinchers, like middle-sized pinchers, and some of you would prefer, for example, the German Shepherd, right? This will be your prototype, but in a way they will be, we can construct the space in a similar manner. Good. So here I also show a different representation, the one that I will be using because it is more convenient for my needs. And I also mentioned that sometimes you don't have one prototype, but you have several prototypes of one concept, and then you're going to have blurred borders. There is very nice work done by Igor Duvan from Paris on vagueness in conceptual space. So it's a huge community working in all sorts of directions. There are users in programming, I don't know, robot architecture, AI, a lot of things is based on conceptual spaces. And I'm going to be using that to see, and those are my drawings again, to try to model how the intuitive concept moves to the formal one. Yeah, well, but going this direction in the context of the concept of computing. Good. So this is my playground, right? So when I was thinking what quality dimensions we are going to, and now we can forget about conceptual spaces, because I will try to speak in terms where I just speak about, properties, qualities, with no deep philosophical engagement to that. So when I was thinking about what there is for a concept of computing, I was thinking that domain is super important, right? No domain, digital domain, something, right? And the second thing is the type of procedure we are going to apply, right? So we can go step by step, and that's probably the most common way of understanding computing in textbooks. But you can put constraints on the procedure, right? So for example, constraints on time and space. And then you're going to land on feasible computing. But you also, and here I won't give you examples. If you have any, please give them to me. But I guess that people working in analog computing, analog continuous computing, they will have examples, some like, you know, implementations in nature. There will be like continuous procedure, right? Like nothing that will be, that you can distinguish to individual steps. I don't know if it's possible, but I imagine it could. And then in the domain, so on the domain, I wrote numbers, natural numbers, or nearby could be some, yeah, well, just let's give it natural numbers. It's a different discussion. Then here I said computable in Turing sense, right, which is more than just natural numbers. Though, if you, well, let's not get there to this discussion either. And then here I put reals in which you can compute. And if you think about Turing machines, it will be somewhere here, right? So it's on natural numbers and it's a step-by-step model. Good, but it is not all. And this is what I learned from, this is my way of implementing physical computing. I wrote representation, but I should probably have written implementation. I don't know, I don't have strong opinions about it. I will have soon, but I don't have them yet. And I imagine that here we are going to have different types of machines, right? So I put slide rule, differential analyzer, PC computer, or neurons. I don't pretend this is the right way. I wanted to make it more complicated at every stage. And then this Turing machine, I kept it here because when I tried to give the third dimension, it would end just over there. But I can imagine that it's like, you know, PC computer, maybe that will be the implementation of Turing machine, but probably you can, you know, construct something simpler and have it there. Good. So, and as I said, it's work before progress. It's like some thoughts that I have about it, and I think it goes into the right direction. But I cannot guarantee for anything that goes beyond classical computing. So I claim that the space of computation is determined by the following qualitative dimensions. So there is the domain, there is a procedure, and there's the representation of or implementation. And in this space, we can place different, there's maybe more of the examples. Here you can put your different understanding of what is computing, and it might be explicative for you to understand, or for us to understand, what computing means. Good. So now safe ground for a while, because I lost my breath and I feel like I really lost it. So now I know what I'm talking about. Church-Turing thesis. Yay! You can think about Church-Turing thesis in different ways. It's usually called the Church-Turing thesis because people don't care which representation, which domain and which procedures are applied, except from some of us. And we are going to distinguish, for example, Turing thesis from Church's thesis. In my work, I was focusing on Church's thesis. If you want to read the paper, it's out there, published since some time. And yeah, and I discussed the problem of axiomatic systems being explications in Carnapian sense, which is not obvious, right? So at the clarification stage, we would say that one might say that computation happens on the level of formal inscriptions when we speak about Turing thesis up to, you know, type token problem. And that we are going to be referring to abstract mathematical objects when we are computing with churches, like Gödel church solution. Good. And at the specification stage, what we are going to do is we are going to distinguish the set of functions, the arithmetical functions, or functions that are defined, possible functions that are defined on natural numbers. And we are going to say, okay, this bunch, those are functions that are computable, right? So this is what we do. The formal counterpart in a specific context that has been chosen. Yeah, well, I shouldn't read that, but this is what we do, right? We say, okay, those recursive functions are computable functions. Well, those functions are like, if you take all the functions defined with, recursive theory language, those functions are computable ones, and we are happy. And then we can prove equivalence between different models. Good. Then we can go for adequacy criteria requirements. I don't have time, I won't do that, but if you want, we can come back to this slide. And then we can show that Church-Turing thesis is a Carnapian explication indeed, right? It verifies everything that I told you it should, and then it goes very nicely on those requirements. Good. Well, conceptual space for Turing computation. Well, I think that the implementation part is not very important, right? So in the domain, we have inscriptions, representations, like physical representations of natural numbers, and then we have step-by-step manipulations determined by Turing, well, in particular, arithmetical functions, computable arithmetical functions. Well, but this is just one intuition, right? And it's already very rich because you can have very different intuitions already at the level of effective computation, right? You can have a feeling that computing happens only on the level of inscriptions. You can have a feeling or intuition that it happens on the level of abstract objects, right? So it's already there, like, you can spend your life looking at that. But there are other concepts of computing, right? There are other intuitions, like, for example, well, a machine, a human, or a human cannot compute in a given lifespan. They cannot compute several functions, right? So maybe, or we cannot compute exponential functions, right? It's impossible. So let's maybe look at how it could be constrained. Right, so this is one set of intuitions that I started exploring, and then there is this analog computing. And when I thought analog, obviously I thought analog continuous. Now I know, I read Corey's papers, and I know this is not the case, and it's richer and broader than that. And I said analog and not analog, but I'm like, this is where I'm learning. But I claim that there is an analog thesis, that we could provide a Carnapian explication and a place in this conceptual space of what computing means to analog computings. Good. So the one that we were looking at, feasible, is defined in a Turing machine in p-time. This is where we already said that we replaced feasible. So we use feasible instead of effective, or we use a different understanding of effective, right? There is a whole thing that you can say about it. So we can claim that Coban-Edmonds thesis is a Carnapian explication, right? So there is a work that has to be done. We, for example, have to address, so in order to have a paper published, so we have to push away or sort out or address at least the usual criticism, which is that the degrees of polynomials are not taken into account, and that despite our dream of being humanly or machinery, well, possible to like relate the machine, we are still having this unrealistic assumption about an actual existence of the totality of natural numbers, etc. Right? But in a way, we can make our checklist, and it will be working. So this is not a problem. But now, and so yeah, when we look at the conceptual space of that, so the domain remains a discrete structure, but there will be a constraint on step-by-step procedure. This is how I see it. And then there is this analog thesis, right? So this is where it's not the procedure or the type of procedures that will change, but what will change are the representations, right? And the step-by-step procedure will remain, unless it won't. Oh, it's hard. So those were my thoughts, right? It's between the beginning of the month and now. So sorry for coming with so fresh thoughts, but they are grounded, right? It's not like completely new. And I think that I can benefit a lot from a discussion here. So I have done this taxonomy of intuitions, and my feeling was, and I'm sorry, there is no mechanic computing listed here. There is no semantic computing listed here. There is no analog even listed here. But my feeling was that we are coming from two different points where we can meet in the middle, or I can more go towards you and you can go more towards me, to recall the Andres questions about what Gualtiero has to say about you know, the computation part, not physical part, but the theory part. I'm coming from the theory part, and I have a lot to say about it, right? There's like thousands of problems that we are addressing. After reading Oron's book, I was thinking that maybe we could say that when you're in this theoretical abstract part, there is something which happens from the inside. So it's like a human experience that we are addressing, right? Because we don't have physical constraints, right? So we are formulating those different types of theoretical computing. Because this is how our mind can conceptualize them for itself without having any physical implementation. And so the problems that you are going to encounter there is, for example, how to deal with non-standard interpretations, right? I mean, how do I distinguish my standard model of arithmetic of you know, non-standard models? I mean, there is no good way except from going very hardcore, very strong logical constraints and logical tools, which still brings us into vicious circles. And there is a problem with the justifications of what is the intended model of computing, right? We try, and this is one of the main discussions which happens in this area, like for me. And this is where, you know, I see well, I wanted to say indeterminacy of computation somewhere in my slides. And when it comes to the physical world, right? I mean, physical computations, this is a completely different story. I mean, it will end up in the same place, and you will be dealing with problems we deal with, and we are dealing with problems you deal with. But for me, it's just that my lack of understanding or the interest of studying that comes from the fact that the intuitions are just elsewhere. You are always in the intended model. You don't have a problem with that, right? It's always there, like this physical device. Well, of course, when computation comes and strikes, and we don't know how to characterize the computing system and how to distinguish that from the not computing systems. But in a way, it's still intended model, right? It's still omega. There is nothing happens afterwards. And yeah, and situated counting, that was somewhere in the discussions with Gualtiero that came out. And I think this is a very good intuition. I have a paper about situated counting, right? How children learn to count. And with Peter Jardenfors, we explore different situated situations where children learn step by step how to count and how to create, thanks to that, the concept of the natural number. So maybe this is more primitive than all these theoretical investigations. Good. So those are things that crossed my mind that should probably be taken. So yeah, so there is this debate. For me, there's this debate about clarification of the concept of analog computation, right? So I learned that it dates to Goodman and Lewis. That continues, that analog was very often related to continuous as opposed to digital. Corey, he makes an attempt to clarify this concept. Philippos also has a paper distinguishing analog and analog when one is physical and one is theoretical, continuous. Paweł Stacewicz, with whom I work, he is making this distinction between analog and physical. I'm going to say about Paweł's ideas a little bit more, because this is where I started my investigations. And for Paweł, what interests him is what is the engineering understanding of computing. And also there is a whole bunch of questions about computing processes in nature, but you know that better than I, so I'll just move to the next slide. So I'm going to tell you what we proposed about this analog computation thesis. And as I said, I think it's a very naive first attempt to see what could be happening. The idea is that there are two types, that analog can be understood in two ways. You know, it's all computation carried by certain natural processes used in engineering, some artifacts, among other teams, and then analog computations are understood as operating on continuous quantities described in mathematics by real numbers. Pavel, he distinguishes AC, analog continuous computations, and ANE, analog, so empirical computations. And what we wanted to explicate, because I didn't see, so the problem, the thing with the analog empirical is that there is no, they are dedicated, right? So there is no one theory, a mathematical theory that would explain them all. So what I was looking at were those A and E's that are A and C's, right? So so this group, and this is, so this thing, I tried to provide the analog computation thesis. So the thesis says that one of the models of ANC computation on real numbers adequately captures what engineering understanding of computing refers to. So it's a bit of overstatement, right? Those that can be described by the ANC, which makes this thesis very weak. But still, well, it's a first step. And thank you. And I was in time. Right.
Thank you, Paula. Yes, Orly.
Thank you very much. It's I find this very helpful. Your playground and the rest of the tools. Here is a question, maybe for clarification. Once, I mean, you start with some intuitions that you very clearly present, and I find some similarity between your project and Ron's in the book.
Yes.
So these are you present things in different ways with different kinds of emphasis, but that's the idea, starting from some paradigmatic intuitions and then beginning to form a notion of computation. And then my question is that by the end of collecting those paradigms and creating the concept, do you think that the concept that comes out is some unified concept or a disjunctive family kind of concept? Is it just things that we intuitively think of as computations and that, you know, satisfy some similarity, vague similarity that justifies, practically speaking, putting them under the title or the heading or the name of computation? Or is this something that strongly unites them and that you can, at the end of the explication, come out with a very clear notion of computation, and then you can apply it for test cases?
Yeah.
So
Thanks. It's a
Yeah.
very good question. So I have at least three things that come to mind. I think that thanks to this framework of conceptual spaces, we might just find a conceptual space for the concept of computing, and those concepts will be differing, right? So I really like this drawing with, you know, the Swiss knife and all those different explications. And when I think about Carnap's methodology, he doesn't say that, but I think it's not contradictory with his standing. So if you explicated the informal concept once, you can make it more precise, right? You can move forward.
Yeah.
You can move to another formal framework. Like, this is why this language tool is extremely flexible. And when I think about Carnapian explications, I really like that Pierre Wagner reading of that, right? That this is the way of introducing new concepts into the language. I like the idea of conceptual engineering, right? Where we engineer, well, I don't think it's that much of an engineering, but it's a different discussion, right? But we are going to get, so what I hope for this from this project, first of all, I want to understand and I want to be able to talk to my friends.
And there were moments where we couldn't. And I was like really trying hard to, make my minds meet, right? And in order to make minds meet, we need to have a common space that we refer to in a way. So it was important for me to make this, to place those concepts in different places and see where they go, what are their problems, what are my problems, because it's all about computing. I don't think this is a completely different thing. I think that maybe sorry, Nahum, if I put too much on your mind, but you're for me the person like incarnating Gödel, saying, oh, we want to have this absolute understanding of computing, right? This is what we would like to have, but in a way, it will be just one of the understanding of computing in my thing. But maybe. So I hope that we'll have a common space for communication, that we are going to be able to see which aspects of computing are important for whom and for sorting out which problems. We are maybe possible to see which problems the other communities address, and maybe they will be somehow, like my voice shaking, I was shaking all the time, but when I was speaking about pan-computing and the fact that, oh, you work always in intended model, and then my brain's like, no, they don't, because they have the pan-computing problem, so they also deal with non-standard models of Omega ordered, but non-standard models.
But I'm not sure that the analogy, can you maybe expand about that? But I also thought I heard some sort of
My
an
shaky
analogy
voice.
between, the status of the intended interpretation. Oh, sorry.
No, but I like this question, and we definitely will talk about it.
Yeah, and then what do you want them? Yeah,
I
okay.
raised my hand, but I wanted to, so yes.
So,
Yeah, I mean, because you just mentioned it.
Okay, so the problem that I dealt with when I was writing my PhD thesis, and then for some time while working on what does it mean to compute, one of the problems was to distinguish, or it's still the problem, how to distinguish the intended model of arithmetic from all others. And here I don't even speak about non-standard models that have all the structure, the skew, behind. I'm speaking about uncomputable models, right? So where your natural numbers are ordered in an omega order, but are represented in a way that you cannot compute, right? It's not computable. And we have those kind of progressions, right? There are uncomputable progressions in the world, we can think of them, we can imagine them, they do exist in this sense. So this is one of the problems that this, theoretical computing deals with. And when I think about pan-computing, maybe this is a similar problem, right? Because there are some things that don't compute. You don't think so?
Because
Okay,
I
good.
think that's exactly what was my question, because I think that the question of indeterminacy of computation, or what precisely the physical system computes, arises within the intended.
So you think it's always the intended model?
I think so.
Yeah, maybe that can be my lack of knowledge of the discussions of pan-computing. That's the thing it can be. It's just, it's like, oh, maybe this is where. Thank you.
Yeah, thanks. One theme in your presentation makes me think of the semantic versus what might we call structural aspect of computation. And both the words analog and digital come from representational schemes. So, in that regard, clearly representation is important, at least etymologically, and certainly historically, conceptually, and of course, practically in our interest in computation. And that's one way to distinguish different kinds of computation is, well, do we use a digital representational scheme for specifically numbers, or a different one, maybe an analog one, where analog means, and comes from analogy, means that the physical quantity here is representing this numerical values. And then there is this other aspect, which has been called by some people structural, that's independent of or at least somewhat more distinguishable from the representational scheme, because you can even abstract away or generalize the representational scheme and say, well, it doesn't matter if you're representing numbers at all. You know, you can represent other things, and you can represent them by some kind of system of discrete states,
Mhm.
and maybe you can still use the same term, digital, which we do. Or it could be, you know, represented another
Yeah,
way, and so that could be an analog scheme. But then you can still talk about, you know, well, what are the components? How are they organized? Do they, you know, they're the physical signature of computation. So there's these structural aspects, and I wonder if there is any kind of clear correspondence between your two types of computation, empirical and the other one, with this distinction, or these are orthogonal.
I think they are orthogonal. I did not first thing tonight. I'm going to implement it in this presentation or in this code. Yes, of course. I mean, I'm very well aware, right? On ours, no, I don't want to say it, but in the theoretical part, this is one of the most important distinctions, right? It's Hilbert-Frege controversy, right? It started probably way before, when you want to have your representations of numbers to have some content and to mean something, and then, you know, it's like children when they learn numbers, they also even this distinction. I have a paper about it, so they might be interested. They will be learning about the content of what numbers mean, individual numbers, but they will also learn about the progression, and this is purely structural, right? It's just like next one, next one, next one, next one. And we know that there is more to that we want to be able to compute on those structures, etc. So yes, definitely, this is very relevant, but I don't think it makes any like the difference between me thinking theoretical, physical, right? I think those are like different type of focus that you're having. Here, like in the theoretical, we are focusing on what we can do and like what we abstractly think about computing. And you're like, oh, does it compute? Oh, and this rock, does it compute? Oh, how can I justify it? And of course, we are going to have same questions and similar answers. But for me, the starting point is just completely different. Thank you.
Okay, thank you. This is a question about your very interesting suggestion that the Church-Turing thesis is a Carnapian explanation. And I'm wondering whether you would go further than you actually did in your talk and suggest that Turing might have had Carnap's ideas in mind when formulating the thesis. And the reason I ask is that Zhao Fan and we very recently found Turing's library borrowing records in Cambridge. Nicely dated, and you know, so he was borrowing volumes containing papers by Carnap at the time he was writing on computable numbers.
That's
So
interesting.
certainly the basis to argue for it.
I think that would be the case to defend, and you know, there are those books about what are explications for Carnap, right? In which framework, in which historical background, where he comes from, and in which context he was developing his ideas. And there are ideas, and there is the book of Baikarus, right, who claims that a Carnapian program is like a revival of enlightenment, right, because he wants to help everyday people, like regular people, to relate to science and to use more scientific language. And this is what explications are for. Eric Heck and Katarina Dulit-Novas, they wrote about it as well. So maybe if you go this way, right, that Turing, he wanted to explicate the mind, right? And yeah, well, now I will just say too much, but I think it's a completely feasible path of development. And please, let's write about it. Like let's write to each other about it, because I would be very interested if that could be defended. I have so much more power.
Yeah, I have no idea whether it can be defended, but kind of because I haven't thought about it yet. But
That's a historical question, right?
Yes, and another connection is that Braithwaite, who was a fellow of King's was along with Turing, was mad keen on Carnap. You know, at that period, he was sort of devoting his career to Carnap and
That would be
exploitation
so
of
great.
Carnap. And Turing and Braithwaite were, you know, they talked. They were both. You know, Braithwaite was working on the intriguing problem as well.
Maybe not by Carnapian explications themselves, but maybe by all the spirit that was there from which the Carnapian explications were born. I think that this is an easy case. After to which extent Carnap himself influenced, that is a historical question that is worth looking at. Thank
There are
you.
things to be explored, yeah.
Thank you. That's exciting.
So I have a comment and a question. Okay. So the comment, the comment is that I would distinguish between computability and computation. I think that what Turing and Church did, they explicated the notion of computability, not so much the processes of computation. And I think, of course, there are related projects, but they talked about functions. The same about the Cobham-Edmonds thesis, that of course problems that you know, might have like polynomial time algorithms that solve them also have non-polynomial time algorithms. So solutions. So so they were concerned also about the functions and not about the
Processes.
The processes. Yeah, that's how it would be. So I would
Okay.
yeah. So this is something this is a comment. And about and my question is about how you compare, you know, what you take the Carnapian explication to be and what Stuart Shapiro calls, I forgot the term that you basically also open texture, right?
Yeah.
And I think in a way, at least Stuart probably is still asleep and we will join us later, but maybe I'm wrong, but it seems that like in the concept of Carnap, we have our intuitions, and then we work on them in different ways, try to and then formalize them, and but the basic intuitions are there, and then you get some form of explication. If I understand Stuart correctly, it's not exactly the case. The whole process is dynamic. You start from a different intuition. The concept is, you know, very vague or something like this of computability, and then the dynamics of process itself. I mean, this explication process actually also changes the original concept in a way. I mean, the end result we have about computability, you know, after Turing's work is different from the intuition we had at the beginning. So there is a dynamic here. So I wonder if this is a correct interpretation of Stuart and Carnap and how you see it.
Well, you know, I have this unpublished paper, got rejected. I never took care of publishing that further, as we all know the story. But the paper is about conceptual engineering, right? And in the introduction to this paper, I compare all those, well, I list them at least. I don't compare them as deeply as you just did. So I just list the different methods that come under this conceptual engineering, right? Like conceptual spaces, open texture, Carnapian explications, they all have more or less the same purpose, right? As when I now started reading more history about the Vienna Circle, that was the whole project, right? Maybe we are just reviving the Vienna Circle in this respect, right? Because the need to make our concepts more precise. Well, this is one of the most common discussions that philosophers have today. So I wouldn't dare now to compare the methodologies and whether, you know, the fact that something becomes a closed texture and there is no open texture concept out there anymore. In Carnap, it's very clear that the intuitive concept remains, right? Like as our Swiss knife, it remains, it's still useful. We will still use it. We will not use, you know, super fancy, very complex concept or tool to do just, bread cutting, right? So yeah, I mean, it's interesting, and thanks for for your distinction. Well, it gives yet another layer to those things here, but that's a good thing, right? Like there is a hope we are going to be more precise. And thanks for recalling.
Okay, we have time for one more question. So Philip, please.
Thanks for this. Look, first, the last slide was really quick for me, so could you go back to the last slide?
The last one. Oh, I think this is. I think this.
No, it was, when you have diagram between the different.
Oh, this one.
So what
Yeah.
are the domains?
Yeah, okay, so I don't know to which extent I belong to this project. This is why I also like I sneaked under it. Yeah, so the idea is that you have like when you think analog, you think analog continuous or you think analog empirical. And this is the main distinction that Pavel is introducing in his work, right? So when you think about those analog empirical cases, some of them will be describable or accountable for in terms of continuous, right? The continuity will be the main concept used to explain what happens in this engineering natural processes, right? And his paper gives several examples of biological situations in which we are like we know that or people claim, and please don't ask me for more details, but the idea is that you cannot really describe those processes in discrete terms, right? So you cannot reduce it to digital computing. Good. So some of them are like that, but not all of them are like that. So they are I and E that are not A and C, right? Because those will be some digital processes, right? Like when you all have all those machines that are like computing something, and the engineers will have a feeling that, oh, this machine computes and not rock, like, right? Like something like making this work. Corey, he has several examples in his paper. Well, they will be there, well, unless you think that analog continue, yeah. So this is the idea.
So I don't question what you would expect about Canadian explication.
About what?
The discussion we have already about Canadian explication.
Yeah, connectifications, yeah.
My opinion, I would like to see your thoughts on this. My opinion has been that the Canadian explication has a kind of arbitrariness because it talks about expediency of different frameworks. And we feel that somehow other models of effective computability like force, lambda calculus, whatever Turing's, they all could be seen as Canadian explications because they all capture the criteria. But then we would think, I think, that Turing's analysis specifically captures something more that is not captured by lambda calculus. By chance or by force or whatever, maybe more by force, but not by real lambda. And so some people think that Canadian expedition maybe it's too crude. Still this. What Church achieved, what the other model achieved, actually, what Turing achieved, and some people suggest that we look at one thing to look at the Kreiser's squeezing arguments. What it means, let's use these because they are less. What I like to is Dimopoulos had this idea about somehow you capture the model in constitutive assumption. And we think maybe we could see that during this kind of conceptual analysis, capture something fundamental about the notion of constitutive assumptions while just different
It's a very good question, and I think that there is, so for non-domestication, you can apply it a lot of things, right? And I think that one of the problems I saw is that you can do too much, right? I mean, you're executing everything, and everything might be considered equally good, equally interesting, etc. But then for some reason, we are making, or I'm making, and people, when they speak about it in the literature, they speak about Turing approach to computing or Church's approach to computing. You had all those, historical and contemporary comments that Turing's way is the best capturing intuitions relating to abstract computing, right? So in this respect, I agree with you that I hope it replies to your question. I agree with you that there is something special about Turing and something special about Church as well. Where you have this axiomatic system which incarnates computation in a well-known formal arithmetic, right? Because Turing is something different, right? Like for me, Church, he provided the mathematicians working in axiomatic systems very nice and important tool, right? So now what would be I still think that it would be interesting to look at other intuitions of what people had about computing, especially because there is this extensional equivalence between all those models of computing, right? They all compute exactly the same set of functions. And it's interesting to look at the intuitions, right, that are at the beginning of the process, and may claim that there is some which are more philosophically fruitful, that are like, I don't even know how to express it now in a spread, but I would be looking. So I don't think that all the intuitions, they have the same value, right? I think that some intuitions are better. Right? Sorry for saying that, because it sounds very xenophobic, but I think that there are some which are deeper, more motivated, born from a bigger context, and willing to explain more, right? Not a Conway game of life. Great, right? But it's one of the models of computing, but right. It's a different purpose. It's very specific purpose. Here we have we want to understand computing. Here we deal with and we land on the same extension. But those are like different,
Okay.
Follow up on this, just very small.
Very quick,
very
because
quick.
we are waiting
Okay,
for lunch.
just-
Yeah.
So in Ron's book, the conceptual space, so to speak, starts from the Turing computation and then extends. And in your playground, all the concepts seem to be on a par. So you don't express what you just said. The
No.
Turing is more.
No, I
simple.
don't, definitely,
Yeah.
and I should take that into account, and I will refer to Oran probably very often in this research. Sorry, I'm very it's very recent that I read the book, and I still don't have it, right?
Okay, yeah. I'll give it to you.
I'm waiting.
Thanks for the hint, yeah. Okay, thank you very much to.